What I'd like to do tonight, normally I start off by asking if folks have seen a total solar eclipse, but now I already know. And that is so exciting, especially for down here in Southern California, where the amount of totality, the amount of obscuration that we get, while it may seem significant at around 70% or so, one of the things that I hope you'll leave with is the knowledge that even 99% of totality is not 99% of the show that you get when it comes to a total solar eclipse. It is literally going to be the difference between night and day, whether or not you are inside or outside that path of totality. If by all means, if you cannot make it into the path of totality, please do go outside, look up, and take part in what is going to be a truly national experience. But if you do have the means, if you are free that Monday, August 21st, I implore you, make whatever effort you can to get up into that path, and you will not be disappointed. In order to try to convince you of that, I am going to read to you, normally I do not do this, but I'm going to read to you the first 2 pages of my handy book, Sun, Moon, Earth, that starts off with that eclipse experience. So, let's see. Totality begins. All right. It's not even lunch yet when something takes a bite out of the sun. It's only a tiny notch at first, all but invisible without my cardboard eclipse glasses. Were it not for the shouts from the crowd around me on this August day, I would never have noticed. But now that I'm watching, I can see the bite grow bigger. It is the edge of our unseen moon. The sun is being eclipsed. It takes 40 minutes for the dark notch to grow so big that the sun is now a crescent, but even with most of the sun covered, the heat of the day is still intense. I take off my glasses and take refuge under a tree. There, in its shadow, I see 1,000 bright crescents swaying in the grass to the time of the breeze in the treetop. Every one of them is an image of the sun, projected on the ground when each tiny gap in the leaves overhead acts as a camera obscura, a pinhole camera. Nearby, children have spotted them too, and begin to yell and giggle as they point and play among the bright little arcs. Had I not known what was happening before, the oddity would certainly have revealed the eclipse in progress above. After an hour has passed, only 20 minutes remain until totality begins. The life-giving nature of the sun is no longer an abstract concept. The sky has grown darker and colors are strangely wrong. The landscape is sapped of saturation. The worlds are aligning. With 10 minutes left, the conditions change quickly. The world has turned to twilight. The shadows of trees sharpen as if lit by a single spotlight. Instead of coming from a round yellow disk set amid the bright blue sky, all illumination now comes from a narrow white crescent in a colorless dark vault. I put my glasses back on for these final moments of the partial phase and can see the remaining crescent shrink as I watch. The crowd rises. Conversations hush. And I notice for the first time that all birdsong has ceased. The birds have returned to their nests to sleep in the unexpected night. An unseasonably cool wind blows across my arm as the temperature drops. The eclipse has become a multi-sensory experience of sight, sound, and touch. So little of the sun is left that surely totality should begin at any second. But I can't tear my eyes away to look at my watch. Even the passage of time seems affected. These last few seconds seem to expand rather than diminish. Suddenly, the sun's thin sickle of light breaks apart into an array of brilliant specks that dance and shimmer along the moon's jet black rim. They're called Bailey's beads, the last rays of the vanishing sun streaming through actual mountain valleys along the curved lunar surface. I finally remove my protective glasses to see them quickly wink away until a glorious diamond ring appears, a single glistening star set in a band of white radiance encircling the moon. Then the spot collapses upon itself and is gone. We have reached totality. Where before there was light and heat, now there is only a cold black hole in the sky surrounded by a coastly crown. The corona, a ring of immense pearly tendrils, envelops the darkness and stretches off into the sky in all directions. It is unimaginably beautiful and only ever visible during these few precious minutes of totality. All around it are the brighter stars and planets, invisible until now. It is a day that has become night at noon, with the sun, moon, planets, and stars overhead all at once. As an astronomer, I know the mechanics of this celestial alignment. Yet in this moment of totality, I fully understand the difference between knowledge and feeling. That is even a shadow of what it's actually like to be there. I've been lucky to see 2 total solar eclipses in my life. I got clouded out for a third. I've seen a number of partials, but they hardly count. When I finally did see that one, back in 1999, I had waited 20 years. I had been a small boy, 9 years old, in Portland, Oregon, when the last total solar eclipse to touch the continental US passed directly over my house in Portland, Oregon. I was really interested in astronomy, yet, because of all the warnings about not looking at the sun, how dangerous it would be, I thought for sure there must be some special rays to come out of the sun during the moments of totality. And so, lest I be tempted, I hid in my house with the curtains drawn. I saw totality on my TV set. The only direct experience I have is just how dark the house got. This fear is something that has been with us throughout, well, humanity. As long as human beings have interacted with total solar eclipses, there has been fear. One of my favorite stories about what a total solar eclipse is the demon, the bodiless head Rahu, who in Hindu tradition would devour the sun. And if the public could go out and raise a big enough ruckus, make a loud enough sound, you might startle Rahu, and Rahu would drop the sun before he'd completely eaten it, and so the eclipse would only be partial. There's other stories. One a little closer to home is from the Pomo Indians in Northern California, and they have this story of this bear that would walk along the Milky Way, and the bear would encounter the sun and have a fight with the sun. And then it would continue along the way, and 2 weeks later it would encounter the moon and have a fight with the moon. The word for eclipse there is sun-bit bear. And the idea, that the thing that I get from this that I really love is that connection between eclipses of the sun and eclipses of the moon. Because today we do know that they are connected, and they are connected by about 2 weeks. That's about half the moon's orbit. And so to see where this comes from, let's talk a little bit about what an eclipse is, the different types that you get for those that may not be familiar. So we have eclipses because we have the Earth, the moon, and the sun. And the sun provides this light, and it casts shadows from the moon, shadows from the Earth. And as the moon goes around the Earth, different bodies get shadowed by other bodies. So for instance, lunar eclipses. How many folks here have seen a lunar eclipse? Okay. The reason for that is a lunar eclipse happens when the full moon passes into the shadow of the Earth. And at that moment, the only light that falls on the moon is light that has managed to pass around the Earth, filtered through our atmosphere. And so at that instant, the light of every single sunrise and sunset is projected onto the moon. If you were to imagine yourself standing on the moon as it enters the Earth's shadow, and you were to look up and overhead, you would see the Earth pass in front of the sun. And at the moment of totality, you'd have this bright orange ring of the Earth's atmosphere surrounding the darkened Earth. Well, anybody on the dark side of the Earth gets to see a lunar eclipse. So whenever a lunar eclipse happens, roughly half the world's population gets to see it. So these things tend to come along pretty frequently, and when they do, everyone gets a chance to see one. Here's a photograph of one such total lunar eclipse. The next one that's going to be visible from our neck of the woods is actually going to be January 31st of next year. Okay. But that's not what we're here to talk about. A lunar eclipse is different from a solar eclipse. And in giving talks around the country and talking to people in various places along the path of totality, one of the things I've encountered is people saying, oh yeah, well I saw a solar eclipse just last year or just a couple years ago. Really? As it turns out, most of these folks think about lunar eclipses simply because those have been in the news. But when you do have a total lunar eclipse, 2 weeks later, it takes a full month for the moon to move once around the Earth. So 2 weeks later, as you go from full moon to new moon, the moon passes in front of the sun. And at that moment, it casts its shadow onto the Earth. So solar and lunar eclipses tend to be paired. But whereas half the world's population gets to see a lunar eclipse, only those folks who are fortunate enough to be within the shadow of the moon get to see a solar eclipse. So this is one of the reasons why they are so precious. Even though they do happen somewhere on the Earth about once a year, it has been 38 years since the last time totality has touched the continental United States. Half the US population wasn't even born yet the last time we had a total solar eclipse. So now there are two different types of solar eclipses. And that's because the moon's orbit around the Earth isn't a perfect circle. It's an ellipse. Sometimes the moon's a little closer, sometimes a little farther away. We've heard about this in a phenomenon that has certainly become popular in the last few years. How many folks have heard about supermoon? Okay. I have zero idea where that term comes from. I have no idea why it has made its way to the popular consciousness the way it has, but so be it. We're stuck with it. So a supermoon happens when you get a full moon right at its closest approach to the Earth. Well, if we think about this, if you have a full moon at its closest approach to the Earth, 2 weeks later, when the moon passes around to the other side, it's going to be at its farthest point from the Earth. And if you were to have a solar eclipse at that moment, the moon is going to be too far away from the Earth to completely block the sun. And so you get what's called an annular eclipse. We here on Earth are fortunate in our solar system in that we alone have a moon of just the right size at just the right distance, so it is almost exactly the same angular size. It appears the same size on the sky as our sun. But because of that elliptical orbit, sometimes being a little farther away, sometimes a little closer, that difference is literally the difference between fully covering the sun and not being able to do so. So during an annular eclipse, you're left with a ring of fire. And we have had one of these in the United States relatively recently. Back in 2012, on May 20th, there was an annular eclipse that passed through the American Southwest. It went over about a dozen different national parks and monuments. I happened to be out at Chaco Culture National Historical Park in New Mexico, Chaco Canyon. Anybody ever been out there? A few hands. A magical place. 1,000-year-old, we used to call them Anasazi. Today we refer to them as the ancestral Puebloan ruins or great houses. And I had the pleasure of standing in one of those. As I got to watch the eclipse in progress right at sunset, and to see the sun turn into a ring of fire as it set behind one of the doorways out there, the hair just stood up on the back of my neck. Parks all across the region set one-day attendance records. Yet, I can tell you, as amazing as this was, it does not even begin to compare to what we are in store for this year. But there is a wonderful tradition of science that has taken place thanks to eclipses, and one of these does involve an annular eclipse. And that takes place back in 478 BCE, so about 2,500 years ago. A Greek philosopher by the name of Anaxagoras happened to live in Athens. And he happened to come up with the idea or realize or heard from someone, but he made the thought that he voiced that eclipses happen because of these shadows between worlds, that the moon passes in front of the sun. And he realized that if that was true, then there's some very interesting things that this must imply. First of all, the sun must be farther away than the moon. If the moon passes in front, the sun must be farther away. Secondly, if they appear about the same size and the sun is farther away, then that means the sun must be larger than the moon. Third, if the sun is larger than the moon and the sun is casting light onto the moon, which casts a shadow onto the Earth, then that shadow should look something like a cone, with the big, large base of the cone being the diameter of the moon, and the smaller part of the cone, the truncated part of the cone, onto the Earth. If you could measure the size of that shadow projected onto the Earth, then you could tell at least how big the moon must be. The moon had to be bigger than that shadow. So, in 478, there was this annular eclipse that went right over Athens and the islands of the Peloponnesus, and he concluded that if he could measure the size of that shadow, he could tell you at least how big the moon had to be. Well, how do you do that? Especially in the age without GPS or without cars that can drive along at 140 miles per hour. I know some of you do. How do you guess? How do you measure how big that shadow is when it sweeps across the planet at over 1,000 miles per hour? Well, he had the idea that if he went down to the port, he was living there in Athens, if you went down to the port after the eclipse and you talked to the captains and the sailors that came into port and you asked them, did you happen to see that ring of fire in the sky? If they said yes, well, where were you when you saw it? A ring of fire is pretty amazing. If you see it, you're going to remember where you were. So by asking the sailors, did you see it? Where were you? Did you not see it? Where were you? He was able to figure out how big that shadow approximately was. And so down through the ages, we have this record, in this case from Plutarch, about almost 600 years later, saying that Anaxagoras says that the moon is as large as the Peloponnesus. Think about what this meant. If a solar eclipse is due to a dragon eating the moon, or a demon obscuring the sun, then there's no real measurement you could make that would tell you anything about how big that demon or dragon happened to be. But if these events are the result of actual physical processes, then for the first time we can do science and we can make measurements that tell us something about the larger universe in which we live. You can measure the size of the moon by simply going down to the seashore. Well, that's an annular eclipse. That's not what we're all here to find out about. Fortunately, there are some solar eclipses that happen when the sun is at its closest approach to the Earth. And when that happens, you get a total solar eclipse. And if you are very lucky to be within the very darkest part of that shadow, the umbra, then somebody standing right there will see the moon completely obscure the sun, and the sun will turn black. It takes about 90 minutes, maybe a little over an hour, for that moon to slowly move in front of the sun. And when it does, at that last instant, as that last little bit of the sun disappears behind the moon, one tiny last fraction of that sun will shine through a lunar valley, or maybe a crater, right there on the limb of the moon. And thanks to modern lunar spacecraft in orbit around the moon that have mapped the moon to incredibly high precision, we can tell exactly what parts of the moon will be there on that limb, and therefore exactly where that last spot of sunlight will occur. And at the minute you see that spot of sunlight, which is called a diamond ring, that will be your signal that it's now safe enough to take your solar eclipse glasses off. Prior to that, the sun shines with 1,000,000 times the brightness of the full moon at night. But when that last little bit disappears, the diamond ring, the total solar eclipse that becomes visible will be no more brighter than that full moon. So to go from daylight to full moon in the course of really 30 seconds is one of the most dramatic changes you will ever experience here on Earth. It is the most unnatural, natural phenomenon you will ever see. And when that happens, two amazing things will stand out. The first is the corona, this ghostly outer atmosphere of the sun. This corona is at a temperature of 1,000,000 degrees. It is the hottest thing you will ever see with the naked eye, barring a thermonuclear explosion. All right. So let's say it's the most hottest, joyful thing any of us will ever see. But the other phenomenon that may or may not be present are these red features here. These are prominences. How these things manifest themselves will depend upon the exact conditions at work on the sun on that day. So I missed the 1979 total solar eclipse because I watched it on my TV set. I had to wait 20 years before I finally got another chance to see one in 1999 when I was an astronomer at a conference in Budapest in Hungary. Even though I did finally get to see one, it was a different one than the one I missed. So, see everyone you can. They will change every single time, and not until the moment of totality will you know exactly what they look like. This was something that was quite a surprise for the first European astronomers to really observe these things as a scientific phenomenon. Prior to that, people had observed solar eclipses in order to learn something about where they were on the Earth. If you knew exactly what time they were to occur because you had done the mathematics of the moon's orbit, you could then predict the instant at which they might occur, and if you were then to measure the local time at which they occur, the difference between these predictions can tell you something about where you are on the Earth. But that doesn't tell you anything at all about the sun. So the first scientist to really look at a solar eclipse in order to learn something about the sun was an astronomer named Francis Baily, a British astronomer, who in 1842 traveled to Italy to see a total solar eclipse. And in his drawing, what you see here on the right, he drew this corona. In fact, he coined the term corona, Spanish for crown, because it reminded him of the crowns that painters painted over the heads of the saints in Renaissance paintings. So he noted this corona, but he also noticed these red flames that he colored bright red here. And after this, he was the one that said, from this point onward, there are so many fascinating, amazing things to learn about the sun that really you need more than just a single astronomer with a pen and paper and some ink. You really need a team. You need a bunch of observers with different telescopes, each observing something different about the sun. And the age of solar eclipse expeditions all over the world really began at this moment. And any nation that considered itself a civilized nation from this point outwards had to send expeditions to any eclipse wherever it may occur around the Earth. And one of the big things that these folks were interested in is, what is the nature of this corona and these red flames? Because if you think about it, these things were only seen at the moment that the moon and the sun intersected. So the question occurred, which one of these objects does the corona and these flames belong to? Perhaps they belong to the sun, and spoiler alert, I already told you they did. Okay, but maybe they belong to the moon. And one could imagine this like a steaming cup of coffee on a winter's morning. You have the rising light coming through the window, illuminating the steam coming up off the cup of coffee. So maybe this was the moon's atmosphere that we were actually seeing. So this is one of the huge areas of intrigue about this phenomenon. Which body did this belong to? Well, the first person to really figure this out was an astronomer by the name of Warren de la Rue. He was the first person to photograph a total solar eclipse with this brand new technology in 1860. He traveled to Spain with these giant glass plates, all of these chemicals, a telescope, a portable darkroom. He went to Spain to make these photographs. And what you see here are the two photographs, one from the start of totality and one from the end. And what you may notice is that at the start of totality, these red flames and the corona all appear to be down here at the bottom of the moon, whereas by the end of totality, they all appeared up to be here at the top of the moon. Well, that's the direction the moon was traveling as it moved around against the sun. The fact that the moon moved against these phenomena meant these phenomena had to belong to the sun. And at that point, people realized that given how far away the sun is, it's 400 times farther away than the moon, then that meant that these red flames, each of these individual ones was vastly larger than the Earth itself. So, what are these red flames? What are these things? If there's a particularly good demonstration of them at the moment of totality, you can see them with the naked eye. A pair of binoculars or a small telescope will reveal them. Even a camera with a telephoto lens will reveal them. But let me tell you something that Warren de la Rue told me. At least he wrote it down and I read it. He took these photographs, the first ever. He discovered where these phenomena belonged to. And yet, at the end of his journal, he said, the moment of totality was so dramatic that if he ever had the chance to see another one, he wished, he hoped he could do it with no equipment whatsoever. So, for all of you out there who have not seen a total solar eclipse before, and are going to see this one this year, do not photograph it. Do not weigh yourself down with a bunch of equipment and telescopes and cameras. Do not spend a precious second of the 120 or so seconds you will be given looking at your camera, figuring out the focus, scrolling through menus. That is a colossal waste of time, especially because somebody else will get a better photograph than you. As folks who've seen them say, photograph your second one. Okay, so let me leave you with that. All right, so speaking of great photographs, here's a great photograph. Miloslav Druckmüller does some amazing work. He's seen a lot. Okay, so what are these red flames? Because that's something that's actually really quite interesting from a historical perspective. These things are giant eruptions of gas off the surface of the sun. And what I'll show you here is a spectrum where light from the sun has been passed through a prism. Its light has been spread apart into its rainbow. And what you can see, and I'm going to toggle back and forth here, notice you've got a bunch of these red prominences here, and then there's this big bright one that's even detached from the limb of the sun. All right, so this is a spectrum taken during the exact same eclipse. You see there's the bright, and there's the one that's kind of super bright and kind of detached. So when you pass the light from these prominences through a prism, you notice that they tend to show up pretty much at one wavelength in the red, another wavelength in the orange, another wavelength in the blue-green, and one out here in the purple. All right, the red, blue, green, and purple, they are the chemical fingerprint, the signature of hydrogen gas. And this is the result of hydrogen erupting off the sun. The sun is primarily a giant ball of hydrogen gas. And so back in the 1860s, when the first people used spectroscopy to look at the sun, they immediately were able to say, the sun is a giant ball of hydrogen and these prominences are hydrogen gas. We have taken a sample of another world, a sample of the star that is our sun. Okay, but here's the interesting thing, if that wasn't interesting enough, this fourth color here in the orangish yellow, it was unlike any other element known. There was no way that hydrogen gas gave off a fingerprint, a line, a wavelength of that color. And so eventually it was decided this must be the telltale signature of an element that does not exist here on Earth. It is something associated with the sun, and so we shall name it after the sun, and we shall call it helium. Helium was discovered on the sun 25 years before it was discovered here on Earth. Now then, there's an interesting follow-up to this story, because you may notice that there is this green light, and this green light doesn't seem to be associated with the prominences, but rather the corona. So the corona gives off this strange green light, and people look to see if they could figure out what element produced this. And eventually they realized that there was no known element that produced that green light from the corona, and so perhaps it's a new element too, and we shall call it coronium. How many folks out there in your chemistry class learned about coronium when you were students? Anyone? Anyone? No. Okay. Turns out it doesn't exist at all. It is iron that has had 13 electrons ripped off of it. And that was the first clue that we were looking at something at a tremendous temperature, far hotter than the sun's surface itself. Our sun has a temperature at the surface of only about 6,000 degrees. And when you look up in the sky at night and you see other stars up there, even the hottest of those stars have a surface temperature of maybe 10,000 degrees. So to see the light of something at 1,000,000 degrees that could rip 13 electrons off of an iron atom, that was our first hint at what the truly amazing, unusual thing the corona must be. How does that energy get up there? And that is one of the things that scientists today are still exploring and trying to discover. So, this is a taste of the kind of science that people have done to learn about our sun. And it is important to learn about our sun because all life here on Earth depends on our sun. If you think about it, every form of life we have here at least that we experience in our daily lives, either uses the sun directly for energy, say plants, or feeds on those plants, cows, or we feed on those cows, which I did at dinner tonight. And so we all depend on the sun in some way for our energy. And so it is therefore important for us to truly understand that giver of all life. But there's other things that we can learn about the universe based upon this phenomenon of eclipses. And one of the most amazing involved Einstein's theory of general relativity. Now, the eclipse that we're going to experience this year is going to travel from coast to coast. The one that I saw, or failed to see, or saw on TV, and maybe that counts, only went through a tiny portion of the Pacific Northwest: Oregon, Washington, Idaho, Nevada, and Montana. This one's going to go from coast to coast, Oregon all the way to South Carolina. This has not happened since 1918, as a matter of fact, a year before the Einstein experiment. And in fact, there were actual astronomers from Lick Observatory down in California who went up to Washington State in order to try to see if they could discover this Einstein phenomenon that was making its way tentatively through the scientific whisper campaign. They didn't. And they were all pretty sure that Einstein was totally wrong. It's crap. And in fact, they even published letters in which they said, oh, let's publish our really crummy results that don't show anything, because when this Einstein theory goes into the dustbin, as it surely will, we'll look even better for having published this way back when we did. Well, laughs on them. So what happened was this. All right, so Einstein had this theory that gravity warped the fabric of space-time, made a pucker in this four-dimensional space that was our three dimensions of space and one dimension of time. So if you had something particularly heavy, like say the sun, its mass would create this pucker, this warp, that perhaps you could detect by watching as distant starlight traveled along and encountered this pucker and curved as it passed around the sun. Here's an example of why a total solar eclipse could be a good test of this. So here we have the sun. It's warping this two-dimensional space-time. We have the Earth right here, and far off we have a distant star. And that star's light travels along this fabric of space-time. It encounters the warp, and as a result, its path is curved a little bit, which means that for those of us here on Earth, we see the star's light coming in from this direction. So as far as we know, it appears as if the star is actually over here. So there is a change in where the star appears in the sky between when the sun is present and when the sun isn't present, or actually isn't present and is. Well, how do you see stars during the daytime? Fortunately, when the moon comes in front. So if you could go out and you could, say, photograph a region of the sky where you knew an eclipse was going to occur, you look at all the stars there, you measure their positions, and then you photograph that exact same region of sky when the sun is in front of it and is suddenly eclipsed, and again measure the positions of all those stars. You could look for very tiny shifts, very tiny changes in the positions of these stars. And that, in fact, is what was done. Arthur Eddington, a physicist, astronomer in England, had been the greatest proponent of Einstein's theory during World War I. And after the war was over, most folks that might have been interested in mounting an expedition to observe this eclipse found themselves out of money, exhausted, trying to overcome the devastation of World War I. Yet, England was able to put a couple expeditions together and travel down. One expedition went to South Africa, the other expedition, South America, the other went to Africa. It's a little island right off the coast. And so these two completely separate expeditions were able to photograph that solar eclipse and to photograph the stars that they saw. And, well, the results confirmed Einstein's prediction. But this would have been just a little footnote. Oh, yes?
Can you see the stars through the corona?
So here's that photograph. So there's the moon, there's the corona, and in between each of these hash marks, and you can't really see it in this reproduction, is a tiny star, a tiny dot. and the positions of the stars. So yes, you can. The bigger the shift, the bigger the change, well, the closer you are to the sun, the bigger the change. The farther away you are, the smaller the change. Fortunately, this is fairly complicated. In Einstein's general theory of relativity, it was a complicated theory. Even some of the folks involved in these expeditions claimed they couldn't actually tell you exactly what was going on. The mathematics was difficult. It was different. But Eddington had done an amazing job of communicating to the press about what was happening, so that by the time the results were presented, you had newspaper reporters breathlessly covering what occurred. And so you had headlines such as, "Lights all askew in the heavens, men of science more or less agog over results of eclipse observations." And as somebody who has written a couple books, I love this last one. "A book for 12 wise men, no more in all the world could comprehend it," said Einstein when his daring publishers accepted it. This eclipse confirmed Einstein's general theory of relativity, but the press covering this eclipse made Einstein into Einstein. He became a star at this point, and that is why we know of him today. Now, we can still see examples of mass and matter warping the fabric of space-time and lensing, causing light to bend, with the Hubble Space Telescope and other telescopes today looking out at distant galaxies, where you can see a blue galaxy's light warped around a much closer massive yellow galaxy. And by measuring the amount of this warpage, we can figure out how much mass has to be there in the nearby galaxy. And it allows us to actually map the distribution of dark matter in the universe. So we are still learning and using these techniques to understand about the universe in which we live. Fortunately, when we look out at that universe and we see that sky full of stars overhead, we can find ourselves wondering about, well, are there any other folks out there perhaps looking at total solar eclipses? After all, we know that we are alone here in our solar system of having just the right moon at just the right distance to allow us to see one. But what about elsewhere? Well, so glad you asked. One of the most amazing bits of science that's taking place today is the discovery of planets around other stars. And the number one method for discovering these planets as they travel around their sun is through what's called the transit method, a tiny little form of an eclipse when a distant planet happens to pass in front of its star, and for a brief period of time, the brightness of that star as viewed from the Earth dips a little bit. And then the planet moves on, and the brightness goes back up. So a very tiny solar eclipse. How many folks saw the transit of Venus a few years back? Okay, exactly the same phenomenon, but now looking at a transit around a distant star. Well, perhaps folks have heard about a planetary system that was just discovered relatively recently called TRAPPIST-1. This was a very small star. It's only about 10% or so the mass of the sun, our sun. But in watching its light, they found not just one, but 7 tiny little dips in its light caused by 7 little planets traveling around that distant star. And by looking at the amount of the dip, you can figure out how big the planet must be. By looking at interactions between the planets that affect the time at which these eclipses occur, you can figure out something about their mass. And so you can begin to learn about the density of these worlds. And one of the things that we now know is that they are all about the same mass and size, some a little bit larger, some a little bit smaller, than our own Earth. It is a solar system of Earths. But because this star is so small, these planets all huddle in very, very close. And so what you see here on the right is an actual map of these planets in their solar system. And what I want to draw your attention to is the scale here, the orbital separations in AU. That stands for astronomical unit. By definition, the distance between our sun and our Earth is defined as 1 astronomical unit. Okay, so we are 1 AU away from our sun. These worlds are 0.01, 0.02, 0.04 astronomical units away from their world, or their sun. So they are packed very, very closely. One of the things you may have heard about in the news when learning about these is that you could stand on one of these worlds, and unlike on our Earth, where, say, when Venus happens to come nearby, Venus appears as a bright star momentarily for maybe a few weeks in our sky. Same with Jupiter. For a few weeks, you get a nice bright star up there. Standing on one of these worlds, you could actually see the neighboring world go from being a star to something larger than our moon. All right, you may think that's cool, but, all right, and here's artist representations of what those worlds may look like. And they've been given the wonderful names of TRAPPIST-1, B, C, D, E, F, G, and H. Leave it to astronomers to name these things. I did the math about 2 weeks ago. If you were to stand on H, and given the uncertainties and the sizes of H and G and how far H and G are away from TRAPPIST-1, from the star, within the error bars, this works. You could stand on H and you could watch G totally eclipse the sun. So, these eclipses would happen. Let's see, it takes G about 20 days, H about 20 days to go around the sun. So, you could stand on H, look up, and watch planet G go from being a star to larger than our moon, in fact, about 3 times the size of our moon, and totally eclipse the sun. Here is the one other world we know about in our galaxy that will experience a total solar eclipse. And given the difference in velocity, those eclipses could last, totality could last, possibly for up to half an hour. But sadly, none of us will be traveling to TRAPPIST-1H anytime soon. So fortunately for us, we can see one much closer at home. And that's the one that's going to be happening this year. On August 21st, 2017, it's a Monday, so we can make a 3-day weekend of this. And totality, like the eclipse that happened back in 1918, the eclipse will be traveling from Oregon all the way across to South Carolina. I do a lot of work with the National Park Service. There are a few parks that are directly in that path of totality, places like Grand Tetons, Great Smoky Mountains. But one of the things that in working with the Park Service we're getting the word out about is every single other park and monument in the country will experience at least a partial solar eclipse that day. So even those of us down here in Southern California, Joshua Tree, will experience something a little over 60% totality. Here in Los Angeles, about the same. All right, so if you cannot travel, this is something to go out and see. And it is something to join in and see because every single person in the United States will get to see this. And in the 90 minutes it takes for that shadow of the moon to travel from Oregon to South Carolina, every single man, woman, and child in the United States will be together within at least part of the moon's shadow at one time. So it is something for us literally to join together in seeing. Okay, so for those of us here in Southern California, if you wanted to drive up to this, the closest place to go would be head up the 5 and get yourself into Central Oregon. So for instance, totality first comes to shore, just actually the midline is here at Depot Bay, but from the size and the shape of the moon, you actually get the first shadow touching land right here in Newport. In fact, at Yaquina Head Lighthouse there. So that will be the first place to see totality that morning. The shadow will then sweep across an amazing wine country of the Willamette Valley. If you are into Pinot Noirs, I highly recommend these folks. One of the things that does make this particularly a great place to see the eclipse, either in the Willamette Valley or just to the east of it, is this mountain. All right, Mount Jefferson. All right, for those of you that may or may not be familiar with the Cascade Range through Oregon, you've got these wonderful mountains with these great big stratovolcanoes, Mount Hood, Mount St. Helens, Mount Jefferson, all perched along there, these big volcanic mountains. From the Willamette Valley and from just the other side out, say in Madras, you will have a view of all of these mountains. During totality, all of them except Jefferson will stay lit up. Jefferson is the only one in the path of totality, so if you are anywhere within view of those mountains, you will see one peak go dark. And depending upon where you happen to be, so for instance, let's see, out here, maybe John Day fossil beds, you could actually have a couple minutes difference in time between when that mountain goes dark, in other words, when the shadow of the moon hits it, and when you go dark. That is literally seeing the moon moving across the landscape. And at this point, it'll be traveling over 2,000 miles per hour. So out here in Eastern Oregon, you get John Day Fossil Beds National Monument. And then farther east, Grant County, beautiful countryside. But I will have to warn you, along Highway 26 there, you're going to encounter towns in which only 2,000 people live, but potentially 20,000 people will be descending. Okay. So like those great solar eclipse expeditions of yore, if you decide that you are going to travel up there, bring gas, bring food, bring water. The landscape, who knows where you'll be able to get any food or water from the locals, because like locusts, all the eclipse chasers may have gobbled everything up. And by the way, in Oregon, you cannot pump your own gas, just so you're aware. Okay, so the eclipse will start in Oregon. It will then travel into Idaho. From Idaho, we go into Wyoming, where Grand Tetons National Park is perhaps going to be the best place to see totality. High, clear mountain air. Certainly, the airport there in Grand Teton National Park is directly on the midline of totality. I am sure there will be people flying in, getting out, looking up, getting back in, and flying off. Okay. From there, we go out to Nebraska, the great big flat Midwest, which I think will actually probably be one of the best places, especially if you're looking to maybe follow gaps in the clouds, if there are any, to be out someplace with a lot of roads and a lot of flat terrain. This could be the place to really get in your car and drive one way or the other if you need to in order to get to clear skies. From there, we get into Missouri. So Mizzou, all right, the University of Missouri is right along the midline of totality. At that point, what started out as a morning eclipse on the west coast, totality being around 10 a.m. Pacific, by the time you get out here, totality is going to be at midday. They will have been in session at this university for about a week, maybe at that point. And so they've actually talked about trying to get the football stadium. And so imagine 70,000 people in a giant stadium with the eclipse happening almost directly above. We then go through St. Louis. Unfortunately, the path of totality cuts St. Louis in half. So the arch is still brightly lit up in this because darkness passes south of St. Louis. And so if you're in the southern half of St. Louis and just outside of town to the south, you'll get to see totality. From there, we go into southern Illinois and Southern Illinois University in the town of Carbondale. These folks are fortunate because it turns out there's going to be another total solar eclipse to touch the United States, and that's in 2024, 7 years later. And whereas this totality goes from northwest to southeast, the 2024 eclipse is going to go from Texas upwards up to Buffalo, New York. So those two paths cross, and they cross in southern Illinois. Carbondale gets to see two. Those lucky folks just have to go outside their door, look up, and they don't have to go anywhere, and they get to see two in 7 years. From there, we go into Kentucky, where you're going to get the maximum duration, 2 minutes and 40 seconds. So not that long. Make every one of those seconds count. At which point you then get into Tennessee. Nashville is going to be the largest city entirely within the path of totality. And that's one of the interesting things about this eclipse this year. It manages to avoid a lot of major cities. This is the eclipse for small towns. But the 2024 eclipse is going to be different. It's going to go over a bunch of major cities. Cities like San Antonio, Indianapolis, Cleveland, Buffalo, Montreal. All right, so potentially many, many more people are going to be able to see that eclipse just based on the number of hotel rooms altogether. From here, we then go across Great Smoky Mountains into the Carolinas, and so we get Great Smoky Mountains in North Carolina, and then out through Charleston in South Carolina, literally racing from the mountains to the sea at over 1,000 miles per hour. So it is for this reason that we're calling this the Great American or the All-American Eclipse. It has actually been about over 200 years, not since 1776, has there been a total solar eclipse that touches one country and only one country. So the last time this happened to the US was back in 1776, and that is literally only within the borders of what would become the US at that point. So this will actually be the first time in which the United States themselves, all of them, get to experience totality. And it's, like I said, when we think about the things that when people have shared in these giant world-changing moments, they tend to be things that are terrible. Things like 9/11 or things like the Columbia disaster, the Challenger. Here is going to be an opportunity for all of us to see something, come together, see totality, see the partial eclipse, but see it together and have it be a moment of awe and joy. And not since, I really say, not since perhaps the moon landings have we had something quite like that. Yes?
You said that the totality was longer in Southern Illinois, 2 minutes and 40 seconds.
Mm-hmm.
What's different? Why is it longer there?
Okay. So for instance, when you take a look at the speed with which the shadow races across the Earth is curved. And so you've got this circular shadow that's being projected from the moon onto the Earth. And when it first touches the US, you're seeing part of the Earth that's curved away. So if you were to move a shadow even at a constant rate, it's going to appear to sweep very quickly along the part of the Earth that's curved towards, and on the eastern shore, curved away. At this midpoint, you're going to be pretty much perpendicular. The speed won't be quite as great. You could even say at that point you're even a little bit closer. So all of these things contribute to giving you a slightly longer period of time there.
The angle of the shadow on the Earth is
different. And that's one of the things that's amazing about total solar eclipses, is because they are not being projected onto a flat surface, as some folks would have you believe. The Earth truly is round. And in fact, our first understanding that the Earth was a sphere comes from eclipses. When you take a look at a lunar eclipse and you watch as the moon travels into the shadow of the Earth, that shadow projected onto the moon is always curved. The Earth's shadow is always a circle. The only geometric object that gives you a circular shadow from any projected light orientation is a sphere. And so
the shadow is round at the center, and at the edges it's more
very elliptical. Yeah. So, all right. So all of these things bring us to this day, this year, this moment, this eclipse. And in order to see to it that there was no other 9-year-old child in the same situation that I was back in 1979, that's why I wrote the book, worked with communities all across the country on those travel posters in order to raise awareness for particular communities, particular parks and places, in order to really hark back to that spirit of, well, I love the WPA and being here within Griffith Observatory in this wonderful building from the 1930s, this idea of using art and science to educate the public about amazing, interesting opportunities. That's what we're doing here today, and that's what we're doing here this year. And so I want to thank you all for coming tonight. I do have books for sale. So I will take questions. Yes. Oh, actually, hold on a second. Let's see. How much?
Oh, we have probably 10, 15 minutes for questions. But first, what I want to let you know that all of these wonderful posters that you saw throughout all the national parks were created by Dr. Nordgren.
Oh. So yes, they're all for sale on my website, tylernordgren.com, and as well as in various national parks and communities across the country. And who knows, perhaps an observatory near you. So,
Go ahead.
yes.
W word, weather.
Weather.
What's your advice on weather?
Okay, so the weather. The part of the country that has the best chance of clear skies that night is Oregon and Idaho. The historical maps of the weather on those days in the morning, because the eclipse happens, totality happens for them in the morning, shows that you've got greater than something like, I think it was 80% clear skies that day. As you travel eastwards, you're traveling into humidity, and you're also traveling into afternoon. And so the probability of clouds goes up. I traveled to the Faroe Islands in 2015 to see a total solar eclipse, and I missed totality by 30 seconds because clouds came up at the last moment, and they cleared 30 seconds after totality ended. And it was incredibly dark, it was amazing, and those of us that tried to make each other feel better said, oh, we had a great time anyway. But for this, I'm going to Oregon. So I'll just put it that way. But whatever the weather may be, it's important to be in that path of totality. So if you have to be in the path of totality out in Tennessee, then Tennessee is the best place for you to be. So, yes, sir.
As far as the attendance, like I'll give you a particular example. I'm traveling to Boise, Idaho, and I'm going to get up early in the morning on the 21st, and I'm going to drive into the path. As far as attendance, what should I expect? Is it going to be thousands of people on a small road?
Okay, so the question is, how many people are there going to be? What are the crowds going to be like? And honestly, we don't have any good way to tell you. What we've been telling communities is imagine the biggest event you've ever had in your town and now double it. And that's probably going to be an underestimate. The last total solar eclipse that actually touched the US was in Hawaii in 1991. And it cut through the southern part of Baja California. People drove south to see it. And in fact, so many people were trying to get into Mexico to see it that my understanding is they actually closed the border at one point. This was 1991. There was no internet. There was no Facebook. There was no social media. You had 3 TV channels, PBS, and yet so many people knew about this that they had problems with border crossings. Now imagine this is something that you don't need a passport, you don't need to go through customs in order to see. There's going to be massive numbers of people on the roads that morning. If you can, I encourage you, if you have to drive into the path of totality, get up in the middle of the night and drive into totality before dawn. And I wish I could tell you better, but that's my recommendation. Other questions?
Will you sign the book that I bought?
Yes, I will be there signing books, and if you've already got a book, I will sign it too. Awesome. Yes.
With regard to Idaho, you're showing maps on the line of totality, but you didn't get into Idaho. Is it on your website?
Yes, actually, what the best places for maps I'd recommend is greatamericaneclipse.com. Michael Zeiler is an expert on graphical information systems. He uses the latest projections of the moon in order to tell you exactly where the shadow is going to be, how it's going to move across the landscape. So he really has the best maps. You can come to my website, and I've got links, but greatamericaneclipse.com is where I'd start. Yes, sir.
Technically, with the traffic system, when those planets pass in front, would that be considered an annular eclipse?
So with the exception of G eclipsing the sun for H, the other ones would not totally eclipse the sun. And if G is a little bit farther away at the other extreme end of its air bars, then yeah, you'd have an annular eclipse. So, yeah.
Now, Travis is 1/10, the sun is 1/10 of our sun, is that correct?
Correct, yes.
Yeah, that was very interesting. And I think I recall that planet means wandering star.
Right, yeah, so exactly. Planet is wandering star. So on that system, to actually be able to see a star, go from being a point of light to a disk, to eclipsing the sun, and then moving onwards. there is no other view I can imagine. Yes?
What kind of scientific experiments are going to be done during this eclipse that you're aware of in your story?
Oh, good question. There's a number of scientific experiments that are being done. So, first of all, there are spacecraft that can create artificial solar eclipses. They have a little mask that they put in front of the sun in order to look at the corona. But in order to do that, that mask has to be larger than the disk of the sun, so that even though we can make kind of a quasi-eclipse picture of the sun almost any time, we are never getting a picture of that corona, that atmosphere, where it intersects the sun's surface itself. So only during the moments of totality do you get to see that inner corona. So there are folks like Jay Pasikoff at Williams College who's been to something like 20 of these things. He goes to everyone with his students, he photographs those. They're constantly looking to see how energy gets from the photosphere, the sun's surface, into that corona. Other science that's being done, you've got a number of folks. Oh, here's a great one. So it's going to take 90 minutes for that moon shadow to go from Oregon to South Carolina. Any one individual is going to have no more than, say, 2.5 minutes of totality. There's a group called Citizen Kate that has purchased 100 sets of telescopes and CCD cameras that they have given out to teams all across the path of totality to go up there. These are astronomy clubs, high schools, universities, to go up there and to make photographs of totality during the 2 minutes or so that they get. But by positioning these teams at just the right position, they can stitch these images together and get a 90-minute long video. The first 90-minute video of totality that's ever been taken, in order to see how the sun and the conditions on the sun change. And again, you will be able to see it going from the photosphere into the corona, all of that, and see it change over the course of 90 minutes. Yes, ma'am?
If you had a satellite that was traveling at 2,000 miles per hour into that path, would that be able to do the same thing?
Okay, so if you had a satellite that was traveling at 2,000 miles per hour and it had just the right orbit that could stay within that shadow, yes, you could. Currently, there aren't any in that exact orbit. I know there's been some talks to see if the International Space Station might encounter totality as it goes around the Earth. One interesting story. Back when the Concorde was a prototype back in the 70s, there was a group of astronomers that actually got the Concorde to follow along the shadow of the moon. This was an eclipse that went over Africa, and it was a very good one. On the ground, you had 7 minutes of totality. By flying along at the speed of the shadow, they were able to extend totality to 70 minutes in the air. There was a group of astronomers that were planning, actually there was an astronomer that was planning on doing this for the public for a 2001 total solar eclipse. He had met with the folks at Concorde. They had identified a plane, they had gotten a captain. They were going to fly the Concorde for the general public along the path of totality across the Atlantic. A ticket was going to be $10,000, which was only slightly more than what it cost to fly on the Concorde in the first place. They had everything written up, drafted, but not yet signed when that plane that they had commissioned was the one that crashed. And the entire fleet was grounded since. So this was not replicated. But could you imagine what that had been like? So, all right, I think we got time for maybe one more. Do we have time for one more?
One more.
One more. Yes, Beck.
Quite a while ago, you said, if something or other, Tennessee. And I didn't hear what you said in between.
If you have no other alternative, then Tennessee is the place to go. Because weather can change. As that shadow of the moon sweeps over you, the temperature drops and it creates its own weather patterns. So, I have been to 2 eclipses where it looked like it was going to be cloudy, and then as totality came on, that changing temperature caused the skies to just open up. And I also saw one go the other direction. So, wherever you are for totality is the best place to be. So for that, I'm going to be then signing books. Happy to talk to you then. Thank you all so much.